I would like to welcome on stage Alexander Oster. And he's the Director of Additive Manufacturing in the Fusion 360 Product Development Group at Autodesk. And he and his team are creating additive manufacturing software, and as far as I know, a very easy to handle software. And you use also generative design, and you were before the co-founder of the additive manufacturing software company Netfabb, which was acquired by Autodesk in 2015. So prior to that, you were at FIT, also one of our members. So I'm really happy that you're with us, and the stage is yours, Alexander.
Thank you for the invitation. I work for Autodesk, and Autodesk is one of the large, large 4 CAD companies. And in this talk, I just want to talk quickly about what we do, because I don't know how many know us, but quickly, like a few minutes. And then I want to talk about something that is not often considered, and I think is a very passionate hobby to talk to of mine, is in order to scale additive manufacturing into the mainstream, we really need to talk about cost, and especially details on the cost. Because I think the quality point is a very important point, but it's just a checkbox item. And I think a lot of the things, especially in aerospace and so on, have proven that the quality discussion is behind us, and now we need to talk about cost. And that's what I want to do quickly. And then I have 2 pieces of the story, and I'm very happy that the Dutch Navy story was there before with the tank, because that proves out that it fits very well to my story part 1, and then I have a story part 2, which is the democratization of Metal AM that we are seeing at the moment that are coming. And I also want to talk what Autodesk brings in order to make this happen, in a way. So if I talk to people in Autodesk in the industry, especially in Germany, they think we are this. So the makers of AutoCAD, which made the drafting board digital in the 80s. So this is AutoCAD 1.1 from 1982. But 30 years have passed since then, and it's not that we are like this anymore in detail, but we are a large software conglomerate of 10,000 employees, and we make 150 different software products for all kinds of design applications. So I think almost every car on the world is designed in Autodesk software. Almost all the, or I shouldn't say almost all, but most of the like famous buildings in the world are designed with Autodesk software. Many of the movies, the special effects in the movies are done with Autodesk software, and AutoCAD, especially in the infrastructure sector, is still a very big product for us, because I mean, to make a highway system, AutoCAD is still a fantastic piece of software. So we make some revenue and have some employees and have many millions of customers. And we are very active in additive manufacturing. So Autodesk has been very active in acquisitions the last 10 years, and also very active in internal developments. And I just want to give a few glimpses what we sell here. So we have Autodesk Netfabb, which is our key additive manufacturing software. That's how we in Germany came to the company. But we also have more fancy software, which is called, for example, Autodesk PowerMill, which is a high-end CNC software, which also can do all kinds of deposition, toolpath control for WAM and DED, and controlling robots up to 22 axes. And then the real fancy things in the composite world, which is very similar. If you look at the composite manufacturing, it's very similar to what we do in additive, just 10 years further. It works exactly as bad as in additive, and you have the same quality problems, and you can't take the composite more than a few minutes out of the refrigerator, or you will screw up your process and those kind of things. So we have a lot of experience there, and here you see like I think a military application where like huge robots are tape layering the components together, and this is also additive if you wish, I think, in a way. So. But I don't want to make too much talk about our special applications. I think what's really important is the cost. And when you go to conferences or whatever, and I think we have seen something like this today, the general wisdom is that additive has a flat curve, so the cost is independent of the quantity. And then you have a conventional manufacturing, like in metal casting. And depending on your geometry and your application, there is the sweet spot, and below the sweet spot, you're cheaper with additive. And above this sweet spot, you're more expensive with additive. And this is very simplified and not the total truth, of course, because you also have fixed cost in additive. So it's not a completely fat line. It's more a less steep curve in many aspects. And if you go from, is there a way back? Yes. So if you go from here to here, you see that this already makes an issue of moving the sweet spot more to the left because we have some issues here. And now the question is, how steep is this line really? And there is a lot of debate about that, and you can have a lot of opinions about that. But of course, if the line is steeper and steeper, then you suddenly, the question is when additive is viable. And if you look at it from this point of view, then it's just a standard discussion of which manufacturing technology is right for my application. And what we often see is a lot of large companies are making the same mistake all over again. We have the fancy technology called additive manufacturing. So let's go to the R&D department and ask what they need to make it happen. And they say, okay, give us 10 million and we will buy 2 machines and we'll hire 8 people. So they spend 10 million. And then the first year they print cubes to understand the process. The second year they print tensile bars to understand the process. The third year they print something more complex to have a showcase. And then the 3 years are up, and then they have the report, and the report says, yeah, we need more money to have more, because we had so many questions, we need to have another 3 years. And the issue there is that this is never going commercial because the setup is in the wrong department, it's with the wrong mindset, and it's in the wrong, it's just not commercially cost-driven. And let's see, we go back to our cost curves and say, okay, we found an application, lifetime, we have a product life cycle of 3 years, like this part here is 500 grams in stainless steel, and we need 300 of them the next 3 years, so what do we do? So 300 is less than 400 of my slide before. This is awesome, so we can make it additive. So we make it additive, so we buy a machine. I crossed out the machine vendor here. It's not against any specific one, it's just a generic concept. So we buy a machine for 500,000, we depreciate over 5 years, so we have 100,000 depreciation per year, which is super cool because our part is $25 in powder and then only $1,000 in depreciation of the machine. So our part cost is 1,025 euros, and this is what we do. And then you go to the manufacturing people and say, hey, why don't we replace this casting part with our amazingly fancy, generatively designed bracket? And they look at the balance and say, yeah, if we cross out the first one, probably. And then you have 3 options, what you can do. Either you don't care, because you have some certification validation costs there in aerospace that are 2 figures higher or 2 dimensions higher, so it's not important if it's 1,000 or 5,000 because you spend millions on everything. And that's why additive, in my opinion, is in medical and aerospace successful, because it just doesn't matter. I mean, people will not. It doesn't matter so much what the part costs because there are many other aspects you need to take care of. The other possibility is, okay, 300 is the wrong number. I mean, let's make 3,000 because then the 1,000 euros go to 100 euros. And that's awesome. The problem is if you make 3,000 of them lifetime, then you're quickly in the, oh, why don't we do in casting? Because casting is cheaper from 500. So you are in this trap. Okay, so we can't do the same part 10 times, but we can develop 10 applications simultaneously. But if we go to a development organization, which is already not so convinced to develop even 1 application, so this is not how large companies work. You can't just do 10 things at the same time. You need to go slow and develop 1 thing and then a second thing. And when that's successful, you get approval from the board and all kinds of stuff. So this is the catch-22. And in my opinion, this is one of the reasons why nothing really explodes in that field, especially in laser powder bed, but also in other places. And if it explodes, it either has it drives a rocket to space or something where we really have a lot of value that is not there. But that's the top 5% and not the mainstream of the 95%. And this is what I think why I want to talk about democratization, which is how can we bring these amazing technologies in the mass market, like on the battlefield or on other fields. And if you look at the top 4, I shouldn't make things like top on slides because somebody will not be happy about this, but let's say we have the top 4 3D printing technologies that I would say are metal powder bed fusion, FDM, polymer powder bed fusion, and stereolithography. These are like the mainstream technologies that are major enough to produce real parts. If you look at them and see what happened over the last 15 years, and we were very passionate about this because like a company like Netfabb was really grown up with this place, and we saw that FDM was the first one that really got the democratization process. So the cheap printers, and I know them because we had them on our booths at Formnext and Euromold at the time, they were really crappy 10 years ago, and nobody thought you could ever do anything, but now, 10 years later, you can lift a tank with these technologies. It happened with stereolithography, so Max Lobowski from Formlabs was very, very keen on democratizing stereolithography, and this went from $300,000 to $3,000. What's happening, that's nearer term. Polymer powder bed fusion, also the cost of entry, there are cheap machines coming to the market, there are like a few, but they're coming more and more, that do laser sintering with diode lasers for $10,000 to purchase. And what is really new, I think that came like last year, the first time on Formnext, is that there are cheap, which means like cheap as a car, not as a house, we always say. Kinds of machines that really print metal with lasers in a reasonable quality. I mean, you can ask all kinds of questions about process control and so on, but like if you scroll that forward 4 or 5 years, then you see something like this, that you have an industrial high-end way. The aerospaces of the world will always pay $1 million for a machine. That's not the big deal. But for the mass market, our prediction is that the cheap machines will have a lot more impact. And you see that with already with FDM and with stereolithography, but also with the others, they will have their impact because they lower the barrier of entry for companies in these technologies dramatically. And the video is unfortunately a bit long, but I couldn't cut it short. And this is, in my opinion, one of the best use cases of the last years that I found for real applications that is scalable in additive. And just watch, I think it's...
Within Heineken, we are located in over 70 countries. We have over 150 breweries and produce more than 250 brands globally. Sevilla is one of the breweries that we have. That's one of the breweries where also multiple brands are produced. We are very interested in looking how digital innovations or new technologies can help us to increase our end-to-end productivity, and therefore we're looking into 3D printing to validate and identify how the technology can help our breweries. We use 3D printing for safety optimizations. Secondly, we also use it to find applications for line optimizations. Finally, we also use it to make very fit-for-purpose tooling to enable, for example, better or safer or quicker maintenance. So we have multiple purposes where we use it for, and I think there will be even more purposes in the future.
We are starting to replace steel on 3D printing parts. With the plastic element, mechanical properties are very similar to the steel. Sometimes it's better. It's very easy to do different improvements. We can reduce the loss of the material. For example, this butter around the conveyor sometimes jam in the sensor to detect the quantity of the butter. This is a problem because normally it's a jam of different butter. Now we create a modification in this sensor in order to it's impossible to produce the jam in this element.
At the moment, we really see that the technology can help us to localize part of our production. For example, when you look at Africa, we see that delivery times or lead times to get parts imported in some countries is really challenging. We are now able to produce them locally in our breweries or very close to our breweries instead of shipping them around the globe. So that's really where we see an advantage. What we've seen so far in the pilots that I've run is that we've significantly seen a decrease of cost, a cost reduction in the functional applications that we found from 70 to 90%. On delivery time, we've seen the same decrease, so also delivery time reduction of 70 to 90%.
Traditionality, in 2-3 days, it's possible to have the part here, and with the 3D printing, it's possible to design, it's possible to print in 8-10 hours, it's possible to run the line again.
In the coming year, we will start up multiple pilots to apply the functional applications we found in Sevilla, but also to find new applications and make sure that those will be scaled across the other breweries that are using the technology in order to leverage the advantages and scale the benefits.
So, like I said, this is I'm the most fan of this project because it's very simple, it's scalable, 120 breweries, they started with one, they will scale it up. It's unbelievable in my opinion, but there are more of this. The most important thing why Autodesk is so interested in this is, if you want to scale these applications to the shop floor, to the car repair shop, to all these mass market manufacturing applications, you need to be able to design the geometries you make. And this is where Autodesk traditionally strengths, and our product, Autodesk Fusion 360, is a key cornerstone of this, because you cannot pay $20,000 for a design CAD tool in order to do this. And Autodesk Fusion 360 is a complete software that can do CAD, it can do generative design, it can do topology optimization, it can do physical simulation, rendering, CNC operations, additive preparation, and it only costs, our target is that it costs a little bit more than an Office 365 from Microsoft, but not much more, so it's $500 per year for everything. And if you look at, if you have taken close contact, so all these parts that you saw in a factory are of course designed in a low-end CAD system, or a low entry-level CAD system like Fusion 360, and it's not only easy to get and easy to purchase, but it's also very easy to use. So with a day of training, and even I am a software developer and I have never used a CAD system in my life, you can do these things very quickly. And then you can put them in the same environment, you can put them on a build plate and press print, and you can then create the toolpath, put it on the Ultimaker just very simply. And this is very crucial if you want to scale it in a mass market, that we also have a mass market design application that fits with it. And that's where we come in. And if you look at the metal space,
oneclick Metal is democratizing metal additive manufacturing. And this pairs exactly with Autodesk's vision of making anything with a robust, low-cost CAD system.
This is an awesome technology, but nobody really can use it. And this is basically where the idea of oneclick Metal was born. oneclick Metal focuses on developing affordable metal 3D printers.
The oneclick Metal machines are very easy to use. You don't need any technical background. By using a cartridge system in our machine, we have a very clean process.
You never have exposed powder, you don't have buckets of powder pouring around, which is the status quo in the industry.
They give you an end-to-end solution that gives you everything from the machine to an unpacking station to a good software integration.
The tight integration between oneclick Metal machines and our own Fusion 360 means that an engineer can envision a product, design it in Fusion 360, and prepare this part for printing in metal.
I log in, I share my project with my coworkers, and I can start working on the same project, on the same part in various iterations. We get a versioning of every part, of every assembly, down to the last click somebody made.
Right now, the situation we see in the market is that you have different applications that all serve a certain purpose. Fusion offers all this in one connected workflow in the same environment.
For us, we first got into contact with Autodesk products basically when we decided to use Fusion 360 as a development tool for our machines and for our products.
not only did One-Click Metal decide to use Autodesk Fusion 360 to make their dream and design a reality, they decided that they wanted to integrate this machine and its processes into our software.
Fusion has a deep integration with Eagle, and as it turns out, we do all of our PCB layouts in Eagle, so we can easily integrate our layouting that we did and move the PCBs into Fusion to integrate them into our switching cabinets or into sub-assemblies where we use our different PCBs. We also try to educate people on how to use this really awesome technology so that more people can use additive manufacturing in their daily lives.
So this is only one company, and we are highlighting them because they also use Fusion for the machine, but there are many companies coming now, and they're selling their system for $55,000 in price in the market. And while this will not be, or can't say that, but while this will not primarily be used for making rockets and turbines on the plane, I think, for example, the holder of the door of an ICE that is defunct, I think such a printer would be much more interesting to use. But that's just one idea. And to conclude it, I just want to show you a few very quick videos. And the geometry is not that complicated, but I have no idea about CAD. And I used 10 minutes yesterday to make something just to show the end-to-end workflow that is really needed for making this happen. So I made this little cover here, and you probably, with some sketching, you could do something nicer. But you can basically just take it, put it on a one-click metal machine or on another machine in the space. You can generate the support structures. You can place it on the print bed. You can generate the support structures either automatically or really manually on the faces. And you can change different settings or save your presets, and the machine vendors gives you settings for different materials that you can apply. And once you have, I just played around with a few of the things, and once you have prepared your build job, you can then directly generate the toolpaths for the machine and send it directly to the machine. And this kind of accessibility is really needed if you want to scale this up into the mass market, and you can simulate it. What is also important is that, I think I have it here, especially in the metal space, additive is very, oh, no, I said something else. Let me show it again. So, and this is all in the CAD system, so this is all very parametric. So if you have once designed your part and your support structures and then go back into the design workspace and then change your part, like moving the holes around, changing the holes, changing wall thicknesses, or going back in the history, changing the dimensions of your part, you can do all that. It's all parametric, backward and forwards. You can go to manufacturing, and immediately all the support structures will update, and you will get a new part that you can print automatically. So it's all stored on the cloud. You can collaborate over continents. You can really integrate it in your development process. And what you also can do is you can integrate with other manufacturing processes within the metal space is really important. So, for example, you can take a CNC machine and in the same module with the same data directly create the post operations on the CNC space in one software. And this is really accessible for every mid-sized company to acquire, because you don't need to pay $50,000 or $30,000 for software, but the base software is $500, and then you can either have for $2,000 per year the full package with all subtractive, additive, 5-axis CNC operations, or you can even have like daily access and monthly access on the state. And as a highlight, what we will release the next quarter is you also get advanced things like process simulation directly in the software. So you can say, I want to simulate if my part performs or if my part will print on the printer, and then you can use a state-of-the-art process simulation inside the software and then also do some adjustments to your print process. For example, you can pre-distort your part. The distortion after the print process is better and all these kind of things. And our big belief is if we don't democratize the full software stack to something that everybody can afford for every engineer in the organization, we will never come out of our niche. And that was my slide. Thank you.
Thank you so much, Alexander. It was interesting also to see how this is improving, and it's getting less and less complicated. I really appreciate that. We have some questions already via Slido. Do we have any questions here in the room? Okay. You get the mic, and meanwhile, I'll ask another question. 3D scan to CAD is a key workflow for preparing obsolete parts for 3D printing. But what's Autodesk's strategy for that space? Previously, Autodesk offerings have changed quite a bit. Autodesk 1-3D, CAD, Remake, Recap, etc.
This is difficult for me to answer because I'm not allowed to discuss future developments. I mean, as public company, we of course always adjusting to the market, and but fusion is the future that I can tell. So that's kind of the
okay. Thank you. Then, did you produce structural components with high contact fatigue?
Is that the metal question for the metal printer? So what I know is about this metal printer, and I mean, I don't operate it personally, so. They use a diode that moves around with a cartridge system, which allows them to do to make much cheaper printers. And this is not specific to one-click metal, it's all these printers. So the surface quality is not as good as with a galvo-based system. That is what you can see on the parts. But the structural quality of the melt pool and the interlay, like the melting of the process, is comparable to SLS. That's what I know.
Mm-hmm.
But I'm sure that academia here can find out the details once it's on the market. Yes.
Coming to academia, Klaus Emmelmann.
Well, hopefully not only academia. Alexander, thank you very much. I appreciate your presentation because you focus on cost and design. And if we have customers, we say, well, you have to change design because you can reduce cost. 50% of your production cost, which you would have with additive, you may have vanished by proper design. Now, this design comes from functional loads. And you mentioned this physical simulations, which you offer already. Yeah. And I think this is the breakthrough, because people don't know how to bionize their products. With CAD/CAM, you can do it, but well, this is not sufficient. So my question, when will we have, for the different applications in mechanics, fluid dynamics, thermodynamics, and so on, the linkage between functional requirements coming from the voice of the customer and translating them into proper designs, being so efficiently and being also so much smarter in cost, and hopefully combined with low-cost AM production. When do you think, because this is something which needs to come from software companies, do you see some roadmap on that?
Oh yeah. The problem is I can't comment on roadmaps, but I mean, our whole storyline about generative design is exactly in that space. And I could have shown amazing videos that I can't at the moment. But I mean, the idea is really that the engineer is supported by these exploration algorithms that give different samples according to some specification and also do the design optimization. What we have in our software stack is very important. There is always a matter of editability you need in the end, because just an engineer wouldn't just accept the black box solution. So you always want, even if it's just a little bit of change, if you change the last 5%, the engineer, it's his design, and that's what we try to cater. So you basically design your constraints, you start the exploration process, so it gives you hundreds of different options for one design, and some options are CNC optimized, 3-axis, 5-axis additive. So this is already possible today in the software. This is no problem. What we are adding is more physics, of course. So it's not only like simple physics, but also complex multi-physics. And what we pushed a lot for is the editability in the end, so that you get a real timeline model of your constraints together with the geometry that was generated, and that you can modify it and go back and forth in the timeline without losing the chain and the boundary conditions. Because it's very important in a daily use. If you have 5 different software packages that don't transfer the boundary conditions between each other, then you quickly don't use it because you lose the trackability and you lose the data management with it. And that's what we offer today, I think.
Very good. Thank you so much. And also for you, Alexander, we have a little present and a little printed lamp.
Thank you.
So thank you so much for your presentation. And if you would like to take a closer look at Autodesk examples, you're more than invited also in our lunchtime to come over to our second hall. And there we have some brilliant exhibits. Thank you so much.